Good evening, guys, or good day, or good morning. Third stream of the day, last one. Unfortunately, today I had a bit different schedule just because a ton of meetings in between that I had to go to without live streaming them, I guess. In this one, we're going to wrap up the paper on hallucinations, and then we're going to see what the next tasks are. Last stream of the day, wrapping up the paper on hallucinations, on detecting hallucinations in empty and tech systems. Well, in empty systems. Sorry for the weird schedule today. Okay, guys. Having said that, let's go back to our paper and let's wrap it up. Again, as a recap, the idea with this paper is that they use this ALTI plus interpretability method, and then they use the source contributions. So the contributions of the source tokens to the output of the decoder to figure out whether the model is hallucinating or not. They do that by the following reasoning. If the contributions from the source tokens are like very small for the output sequence, that means the model was not paying attention to the input source sequence, and thus it has likely hallucinated. And that's kind of the main gist of it, basically. And then there are also these other methods like laser, where basically you take the output sentence, the translation, and the input sentence, you embed them using, for example, laser, which is this basically model that we also use for mining data in machine translation. And if the 2 points are of high similarity, if they are in proximity to each other, that means that they are very similar, and thus the translation is likely not a completely bad hallucination at least. So it's not going to be detached or fully detached, strongly detached, whatever the terminology is. Having said that, let's wrap up the paper. So, for each of the methods, figure 2 shows distribution of scores. For fully detached hallucinations, strongly detached hallucinations, less severe errors, and correct translations. So now let's see when is it easy to detect them. So fully detached ones, so you can apparently see that let me see, these have very high scores. I guess that's gonna be the main way they figure it out. Let's just see what's on the x-axis. Let's continue reading. So ALTI and SecLog prop show similar behavior. Errors are distributed similarly to correct translations. So again, ALTI and SecProp. So errors are distributed similarly to correct translations. The correct translations are the gray ones. Okay. And the scores for partial strongly detached hallucinations have bimodal distribution. So that's the red one. At a high level for the model, some partial hallucinations look more like full hallucinations and some more like errors. This observation can motivate future work. It would be interesting to understand which types of these hallucinations behave one way or another, specifically whether it depends on detachment or more simple patterns such as, for example, the proportion of hallucinated tokens. Okay. Let's try and understand this. I'm not sure why do you create a plot without labeling the axis? So, okay, apparently the y-axis is score, and then the x-axis is what exactly? How do they measure? Let me think for a second. What could this be? Okay, got it. So from 0 to 1 is probably 1. No, wait. This doesn't make sense. I wanted to say 1 is like, this is certainly a hallucination. 0 is like, this is not a hallucination. And then we see that the fully detached ones have scores lower than 0.5. And then here, yeah, this looks like it's from 0 to negative. So that looks like log probability, which is always going to be negative. So if we have very if the log probability is around -1. So this is kernel density estimation. Okay, that makes sense. So with high likelihood, these catastrophic ones are here, and they overlap here significantly. And especially in ALTI, correct translations and errors almost perfectly overlap. So there is no way to actually understand those, but there is way, you can always be certain that if you're around 0.6, 0.7, you're not fully detached hallucination. You might be strongly detached, but you're not fully detached. Okay, that's kind of the reasoning there, I guess. And let's see some better ones. In some better ones, like this one, CHRF and Comet, which are basically your usual, you have to have a reference, and then you can compute the score. And if the score is very low, that means they're very dissimilar from the reference translation, which means you're very likely to be fully detached hallucination. So if the score is very low, then there is a high likelihood of and that's how you can figure it out. That's kind of the reasoning there. Okay, Comet, blind to error severity. We see that Comet and Comet QE scores do not provide separation between hallucinations and less severe errors. Let's see Comet and Comet QE, Comet and okay, there is a big overlap there between the mode of the red one and the brown one are aligned. This agrees with previous work, noting that since quality estimation models are mostly trained on data that lacks negative examples, comets may be inadequate at evaluating poor translations in general and hallucinations in particular. What is also expected is that compared to reference-free Comet QE, the overlap between the scores for correct and incorrect translations is much lower for reference-based Comet. Okay, so the overlap between the scores is much less for this one. Correct and incorrect. So here are the correct ones and incorrect ones. CHRF exhibits a behavior similar to Comet. LabC ranks hallucination severity best. So here is LabC. Okay, this one definitely has a very separate modes. Probably the least overlap out of the ones that are not oracles. LabC is the only detector with a clear order between full, partial, and translations without hallucinations. That's very cool. As we mentioned before, this is expected because only LabC is trained to rank translations. Interestingly, for laser, modes for the three distributions are also ordered. Unfortunately, the distributions themselves overlap significantly, which makes laser not a good hallucination detector. Both LabC and laser ignore most of the non-hallucinated translation errors. X and Y, no middle ground. Finally, we see that distributions are very peaky and concentrated around 0 and 1. This is expected. X and Y's decision is always binary. While this provides good separation between fully detached and correct translation, it is hard to estimate severity. So it's not really nuanced, right? X and Y. So okay, you can see here it's very bimodal. Okay. Detected pathology types. Now we come to more fine-grained categories and look at detected pathology types. For each method, we say that the translation is detected if it is contained in a fraction, for example, 10% of the hallucination dataset corresponding to the lowest scores. So for each method, we say that the translation is detected if it is contained in a fraction of the hallucination dataset corresponding to the lowest scores. Okay, makes sense. Then we look at the distribution of pathology types contained among detected examples, figure 3, and recall for different translation types with respect to the whole dataset. Okay, the three best methods are similar. Figure 3 shows that all T, LabC, and X and Y select similar pathology types. Figure 3. Okay. For them, flagged examples consist mostly from fully detached and strongly detached hallucinations, along with other errors. Laser is an outlier. Laser behaves differently, and instead of focusing on pathological translations, it flags correct translations more. This explains its poor performance on detection mentioned before. XNLI flags under generations. Interesting. So that's the peak here. You can see on the left side. This makes sense. These criteria are symmetric, and if we swap the source and the under generated translation, the longer source can be seen as a hallucination. Okay. Fair enough. Fully detached are the easiest to detect. No shit, Sherlock. As expected, fully detached hallucinations are the easiest to detect. All methods detect them entirely when taking 20% of the hallucination dataset. And they're most frequent pathology type among the examples flagged by the best performing methods. Overall, our findings confirm the conclusions of this work that oscillatory and strongly detached hallucinations are more difficult to detect, and improvements with our methods mostly come from these types of hallucinations. Okay, so distribution of translation types when selecting the worst 10% of the dataset according to each metric. In the original dataset, these types were annotated in a multi-label manner. For example, the same translation could be annotated both as oscillatory and as a named entity error. To assign a single label to each translation, we chose the most severe pathology type, with severity increasing clockwise from correct to fully detached. Okay, so got it. But what's the actual ground truth? Why didn't they set the actual ground truth for the 10% of the dataset? What's the percentage of fully detached versus I see only baselines. Okay. Recalls by translation types when selecting the worst 20% according to each metric. Here the types are presented in a multi-label manner, i.e. one translation may contribute to multiple axes. Okay. Very weird plots. Why wouldn't you put a ground truth there? Laser is an outlier. Let's see figure 4 again. What do they say here with respect to recall for different translation types? Okay. Finally, let us come to the second part of the detection rewrite pipeline. After flagging a translation as likely to be hallucinated, we want to generate several alternative translations and select one of them based on some criterion, i.e. by re-ranking the hypotheses. This general framework has 2 degrees of freedom. 1, generation of hypotheses, and 2, re-ranking approach. We show that for generating hypotheses, simply applying MC dropout outperforms more involved methods such as diverse beam search. For re-ranking, we can match Comet QE with internal ALT-T and improve the hallucination rate by using LabC. In this section, we explain the setup for experiments. Okay, so metrics. In our experiments, we use several metrics. First, we use the quality evaluation metrics commonly used by the community, for example, Comet and Blue. Additionally, we use the 2 best metrics for hallucination detection, LabC and XNLI. Okay, we show some of the metrics in the main text and the rest in the appendix data. We first analyze the impact of our method on translations of different quality levels. For this, we randomly sample 150 sentences from each of the following groups of the hallucination dataset: fully detached, strongly, all other translation, and correct. We apply all versions of the hallucination mitigation algorithm to to these 600. Note that in a practical application, we would apply the mitigation techniques only to the translation labeled by a detection algorithm as a potential hallucination. We simulate this later in section 5302. Okay. To generate alternative hypotheses, these guys use Monte Carlo. This means they leave standard beam search inference intact and achieve variability in translation via activating model dropout at inference. Huh, interesting. A natural question is whether using other generation strategies can give better results. For example, if we use beam search specifically designed to produce diverse translations, can we get better hypotheses? To test this, we use the following methods. Default, standard decoding without re-ranking. I have beam search with size 5, where we pick only the top one candidate. So standard decoding without re-ranking, where they only pick the one candidate. Then beam search with size n, and then sampling from the predicted distribution from the whole, and sampling with P80 from the 80% of the distribution, and then diverse beam search with beam widths 1, 3, and 10. I'm not sure what this method is exactly. And then diversity coding with diversity rates and Monte Carlo dropout, and iterations of a greedy search with dropout, and MC beam, the method used in this work, and iterations of beam search with dropout, each with size 10. And is 10 is all in all experiments. Okay, let's see the impact in figure 5. They say to disentangle the effect of generation strategy from the subsequent re-ranker, we show the results for all combinations. As re-rankers, we consider Comet QE and the methods proposed in section 3. We see that the MCB method clearly outperforms all the others. This is interesting for two reasons. First, MC dropout is easy to use. One has to apply standard inference with dropout without other changes to the implementation. Interesting. I don't think I've ever seen anyone applying dropout like this for beam sampling. Next, differently from modifying the coding strategies, here variability in hypotheses comes from model predictive uncertainty. This is one more evidence that understanding model inner characteristics can be beneficial in various settings. Based on these results, in what follows, we generate hypotheses with beam search with MC dropout. We also check whether generating more than 10 can improve the performance, the overall results. Figure 6 shows that final Comet scores depending on the number of hypotheses. Okay, so the more you generate, the better it is until you hit maybe 30, depending on which one. Okay, we see that the scores increase with more hypotheses and do not saturate at 10. This implies that in case when the quality of the translation is much more important than its computational cost, one can potentially improve the quality by generating more candidate hypotheses, assuming that Comet scores are good, nicely predictive of the actual translation, which depends, I guess, on the language, because this is a neural score. Okay, and then apart from detecting hallucinations, the methods we propose can be applied as re-rankers in the detect then rewrite pipeline. Can be applied as re-rankers in the detect then rewrite pipeline. Okay, let's see the plot above. So different, I guess on the x-axis here are different re-rankers. No, this is the re-rank. And this is the different ways of generating. So this is sampling all MP80 and then diverse beam search and then Monte Carlo dropout, okay. And just default beam search. And then using for re-ranking, and apparently the best one is what? MC beam with XNLI apparently. Show scores for the final translations. Okay. And then Comet, Alti, XNLI. So what changes? Wait, There is the generation, there is the re-ranking, and then the scoring. Okay, so re-ranked, so generated with X, and then re-ranked with this, and finally scored with X and Y, I guess. Okay. And then there is this one, more hypothesis, better scores. Figure 5 shows that regardless of their generation method, LabC is the best re-ranker. So LabC is the best re-ranker. Let's go for LabC. Okay. And it performs notably better than the strong Comet baseline. Apart from the average results, table 2 also shows Comet scores for each pathology type. We can see that re-ranking with any method is better than no re-ranking for all groups of original translations. Compared to the Comet QE baseline, LabC improves the scores of for hallucinations and correct translations, but drops quality for other pathologies. So improves the scores for hallucinations and correct translations, but drops quality for other pathologies. The only internal method, ALTI, performs better than Comet QE for fully detached hallucinations, but is inferior when looking at other translation types. It means that ALTI is very sensitive to the most severe pathology, but not capable to rank relatively good translations. Data. We're almost done, guys. To confirm the results of automatic evaluation, we perform manual annotation. For each of the methods, their translations of the same 200 source sentences. What? For each of the methods, we annotate their translations, I guess, of the same sentences. These sentences were randomly sampled from the hallucination dataset with the distribution of pathologies roughly mimicking outputs of the best detectors, figure 3. Overall, for 55% of the sentences, their original translations are labeled as hallucinations, 25% as errors, and 20% as correct translations. Guys, give me just a second. I have to open up the door. Just a second, I'm coming up. Okay, we're back. So again, to confirm the results of automatic evaluation, we perform manual annotation. For each of the methods, we annotate their translations of the same 200 source sentences. These sentences were randomly sampled from the hallucination dataset with the distribution of pathologies roughly mimicking outputs of the best detectors, figure 3. Okay. Overall, for 55% of the sentences, their original translations are labeled as hallucinations, 25 as errors, and 20 as correct. We did not select these sentences with any metric because it might affect the results of affecting this metric as a re-ranker. We'll leave comparison of all combinations of detectors and re-rankers to the future work. We compared the original translations and 3 re-ranking methods, the baseline Comet QE used in the overall best re-ranker LabC, and the only internal method ALTI. For each source sentence, the 4 translations were deduplicated and shuffled to avoid annotator bias. The resulting sentence pairs were given to 3 annotators who labeled them with 3 categories. The labels were aggregated by majority vote. In case of ties, 20 out of the 602 sentence pairs that were left after the duplication, we pessimistically assume the hallucination. Further details on the annotation guidelines, blah, 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 reported in the appendix. We evaluate the statistical significance of the pairwise differences in the proportions of correct and hallucinated translations using two-sided student tests for two related samples with 5% confidence level. Results. Annotation results are shown in figure 7. All re-ranking methods reduce hallucinatory rate by a factor of 2.5 to 3. Interestingly, when looking at hallucinations, internal ALTI performs on par with Comet QE. The differences between these two methods are not statistically significant. Comet QE, however, has less errors. This is expected. It was trained to distinguish correct translations from errors. Coming to LabC, we find that it produces slightly less hallucinations than other re-ranking methods, and more correct translations than ALTI. These differences are significant at 5% confidence level. Overall, by using a sentence similarity from LabC, we improve both hallucinations detection and alleviating hallucination at test time. Note that since Comet Q is the state-of-the-art quality estimator, it is a very strong baseline for the re-ranking stage where the goal is to find a better translation. The fact that we can match Comet QE's hallucinatory rate reduction by analyzing model internal workings has value from different perspectives. For research, it can motivate future work on model understanding. For practitioners, it means that hallucination mitigation methods are not limited to language pairs where external models such as Comet QE exist. Model understanding might be enough. Okay, so that's kind of the basic difference between these models such as Laser or Comet QE or LabC versus ALTI. Like Laser, you have to train it already for a certain set of languages, and then for ALTI, you can just use it always because it's just a property of the model. That's what they refer to as inner versus external. How is one supposed to do effective research in the field without access to high VRAM GPUs? I currently have, yeah, it's tough. It is tough. You can check out the work from Tim Detmers. There are people who are trying to do amazing work and go around those constraints. Quantization, 4-bit, you can do stuff like 4-bit quantization research or whatnot, but like you definitely need more than what you have with 6 gigabytes. That's way too small. But with like 1 or 2 GPUs, you could already do amazing research, I think. Okay. Before ranking. I might be missing out something, but like it feels like, so they show here what's the output of ALTI, they show what's the output of Comet QE, they show what's the output of LabC, but where did they show the actual ground truth? Like I'm a bit confused about most of their charts. I've never read any papers in this field, so I guess just exposing myself to terminology and understanding some high-level ideas without understanding many details here helps. At least I know where to look for, what to look for if we start having to deal with these things. And I guess I'm not sure. Can you do this like at inference time? Probably not. If you have strict like latency constraints, if your customer submits a request and you have to return it in like 300 milliseconds, then running something like this might be too expensive. Yeah. I'm not sure how expensive. They didn't mention no mentions of like practical use cases like the one I just mentioned. How much does it, like how long does it take to compute this? I guess, let me think. They did show the formula in the previous paper. It's just like a bunch of matrix multiplications. So it might be, potentially even might be done in parallel. to the inference, and then at the output you get the final score, and then you can use that to figure out whether translation is like a complete, like this fully detached translation. That's kind of how I understood it, at least. Okay. Let's remove these papers. Paper reading list is now empty. And what are we left with? I was looking into parallelism a bit today. I did have some issues to understand how to reduce the peak VRAM with the FairSec, i.e. fair scale, because they should be doing like they should be doing parameter sharding, but I don't see the memory being reduced. It looks like they're just, the models are completely materialized on both GPUs I have. I did do this. I did submit an issue earlier, I think in the first stream. Yeah, this is an issue where we need to run more tokens. Let me quickly check something. How many epochs do they use to train NLLB? I guess they have a ton of data. So our best model was trained with softmax loss over 2 epochs with the learning rate. Is this even the right model? This might be language identification detection. Yeah, this is LID, end-to-end encoder evaluation. We use a 12-layer encoder and decoder and train for 100 epochs. Okay, again, this is laser potentially. Yeah, this is for mining. Let's see whether they mention, I think this might be it. We fine-tune on that single test for 50 updates, which is 15 to 20 epochs. Okay, this is over the NLLB MD dataset. This is again what we are looking for. So they didn't mention the number of epochs, but they did mention the number of updates, which was around, I think, 300,000 number of updates. Yeah, we trained the 128 expert mixture of experts model and set this to 300,000 total number of updates. And they have like a bucket of one batch is like million tokens. So what's this? This turns out to be, so is that like 300 billion tokens? Yes. So 300,000 steps, and then add to that million. So that's 300 billion tokens that their model has seen during training. That's a lot. That's a lot of compute. And they did mention that they have like 50,000 something GPU hours on A100. Yeah, that's a ton of compute, guys. Talking about having GTX 1060, that's, you need a bit more to get to that compute. A couple of lifetimes to train this model. Okay, so let's see what we can do tonight. Understand the details behind the computation in Sacred Blue. Yeah, man. Understand the details behind the computation in Sacred Blue. That might be a fun experiment. And then we might enable Sacred Blue during training. That would be cool. Or sampling text during training. And then we need to analyze the data. Let me see what this guy has done with somebody, this person. I don't know what's his name, but he's done some cool work apparently with analyzing the tokens. per utterance. So obviously we would expect English to be up there. Lower number of tokens. What's the utterance? Oh, nice. Nice. He's done this literally during the... Awesome. He's done this literally just for when I wrote that somebody should do this. What's massive PT? Ah, that's just the checkpoint. Tokenize and analysis. He took the Amazon massive and then the tokenizer here, and then he mapped it for each of the languages up there. And then display those. Nice. That's cool work. Hey, well done. What's up, man? Map to letter language code to either BCP 47, which is the code format we use throughout Open NLLB, or just human readable names. How many lengths do you have here, etc. Okay, but it looks like it's fairly evenly distributed. It's not like, yeah. Grab some super low resource length and compare it to the high resource ones and see what's that difference like. Will some of these words, will some of these languages have words that are completely split into characters, or whatever is the terminology for the smallest unit of text in that length? Okay, so where did we stop? So I want to do one of these two now, honestly. I think others are going to handle this task. I'm going to focus on this. Let's try and add this to our training routine. Sampling, like we do validation, we get the loss, but we don't save the actual sample tokens. We can maybe do that. Instead of discarding that. What do you guys say? And then we can go and play a bit with Sacred Blue to understand it. Let me see how we can do that. Let me open up the VS Code. Here's FairSec. And so during training, By the way, let me quickly just check whether I messed up anything. I did play a bit with modifying the files earlier today. Do I have anything here to do? Set this one back to this number. Okay. Whoops. So I think that's the only to do we had here. Everything else remains the same. Let me just see whether we messed up anything. I don't think so. Okay. Looking good. Let me see whether I have any file modified. Whoops. Let me just change to somewhere here. Copy path. Go here. Navigate there. Clear. Git status. Let's see what we changed. Okay, this can be ignored. This can be ignored. Just a bunch of YAML files. Generate multi has been a bit different, but we don't care about it. It's not in the training code path. Checkpoint utils, we have to revert this back. So we just have to go and do git checkout. That was just a change that I introduced to support Megatron. We can update that to the head. And then here, custom metrics, we can ignore that. Temporary custom eval, we can ignore all of that. I think we're good, guys. This is it. Okay, now we have the correct training code path. Now that we've done that, let's go to train. We just go to train here, go to the train step and enter here. So what I would love to do is during the training, why not every now and then save the like sample tokens and detokenize them into actual text, so we can follow what's going on a qualitative level during the training. That would be cool. Like every now and then do that. I used to do that when I was training GANs or some of those visual models. You want to see the generations throughout the training. Okay, so let's see here. Append, blah, blah, blah. Where is the main loop? We're inside of train step. Where is the forward? Multiple gradients. Okay, this is already after we've done the training step. This as well. Okay, here it is. So it's like task specific. Let me just do something like disable breakpoints. What if we just appended here a bit more data or something like that? We can maybe modify it. Let's go to train. Let's kick it off. Let me just make sure we have only 6 here. Otherwise, my stream will start glitching. To do. Reduce the number of layers in the transformer, kick off the training run, and wait while we hit the breakpoint. Then I'm gonna see how we can add that without sacrificing the performance too much. That would be an amazing addition. During training, if we were able to see, hey, here's how this text looks like for this particular language at this number of updates, that would be cool. Get a better feeling for how loss correlates with the actual performance we care about, right? F5, enter here. Model train. Let's go. So here is the output. Criterion logging output. We might be able to change the logging output. Hit F5, enter here. Okay, so the net output is gonna be here. Okay, enter. Again, same here. Enter here. Go here and enter. So if we stepped over this, okay, cool. We can now compute the loss. but the net output looks like this. Why not just, let me see, net output is what? There is a ton of inner states in there. Let's see what exactly do we have here. So we have, what's the type of this? Is this just a tuple with a ton of things? If so, what's the length? Yes. So what's the length of this? 2. Okay, so let's grab the first one, the first element, and see what it tells us. The first element is unsafe view backward 0. What is this? What's the shape of this beast? Okay, 56, 34, and then the last one is the number of logits, because that's the size of the SPM 200. Okay, so given this, yeah, this won't exactly work. We'd have to actually sample. I can't just reuse it like this, obviously. We have to autoregressively sample a sentence every now and then. How could we do that? Okay. Out of curiosity, what's the number 1? Okay, it looks like a dictionary with a ton of keys. Inner states, gate loss, attention. Okay. So what we actually care about is in the validation, not here. Let's exit from here. Let's exit from here as well. Go all the way up there. Exit from the train step even higher up. Let's go even higher up. Even higher up. Train step. So every now and then we'll hit the validate and save, right? And here is where the actual magic happens, in the validate method. What if we could every now and then just call a custom function that would not just validate but also sample? So let's hit F5. Let me just remove all the breakpoints and put this one only. Hit F5, get to this particular location. Hit F5, get to that location there. We might have to wait a bit because, wait, I'm gonna change the long JSON a bit. I'm gonna just make the intervals be, the validation interval should be like 100, so we can quickly hit it. So here it is, and then let me add a to do, otherwise I'll forget. To do restore 2000, the validate interval updates, and the validate interval, these two. Okay, now let's trigger the run again. You don't like VS Code's debugger, really? You're like the only person in the world I've heard say such a preposterous thing. Spider, wait, really? Spider IDE? Like VS Code, I think, is universally considered to be the best. The best IDE. So what do you get from Spider that you don't get from VS Code? This doesn't look as good as VS Code. Okay, let's go. Waiting to hit the validate function, and then we can see what to do here. Enter here. Let's see. So for each of the subsets, we grab the validator, the validation iterator, and then progress, and then validation step inside of there. I don't think we'll be able to reuse this, but I think I have an idea what we can do. So prepare the sample, and then we do the validation step through the task. Okay, so we don't want to do any of this. We want to do, we basically want to do generate. So let's go to generate.py. And let's see how we've done it here. So once the model is loaded, generator, prepare for inference. Let's see. Okay, we load the models. And then for all of the models, we put them to CUDA, we prepare them for inference. Let's quickly recall what exactly generate does with the model. So we can reconstruct this in our training loop and then have the sector blue and the generation there. So let's think. Let me open up JSON. Let me open up generate method. And I think that's the one. That's the only generate method that we have. So shard languages, blah, 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 valid BPE, sentence. We don't have to change anything. This just remains this like this. We can just maybe make sure, is this Hindeva? Yes, we're using Hindi. So we can just go like first run. Let me see whether this directory can be used. So first run, no cap, Hindi Deva, best valid. Okay, let's go here. Let's just delete all of these. And now let's go to the generate. So generate, exactly. Select the generate config and run this. Let's wait until we hit the prepare for inference. Let me see what exactly the prepare for inference with the config passed as the argument does to model. Which properties, which internal model properties does this modify? Let's see. F11, enter here. Okay, if no beamable, otherwise return false. If false, then retrieve, I guess, beamable, beam size is 5. Need attention, none. Make generation fast. Interesting. Let's pass in the this. Okay, and then if instance of mixture of express layer will never hit this because we're not using MOE. Apply, remove weight norm. Prepare for inference. Dude, prepare for inference calls you Like, okay. And then apply make generation fast. And then train should no longer be used for training. Huh. Can we just set it to eval and run without any optimization? Will that change the actual output? The results, I'm not sure. Let's see, let's enter here. Apply. Make generation fast. So it's mostly going to just do this. Let me remove this. And let me get here. So it does nothing, literally nothing. And then apply this one. Make generation fast. Only if this happens, then we go in here. Otherwise, we go to eval. Okay, so name, prefix, encoder dropout module. Make the generation fast. Let's go here. Huh. So basically, because this is retain dropout, always false, this never happens. Okay. So this is all of this is just doing nothing. So the only thing that we do is self-eval on the model. And then train. Okay. This will never happen as well. Exit, and that's it. We're done. Okay. So I think the only thing we have to do is just specify eval mode. And then let's go here, model. Okay. We can copy this piece of code. And then build the generator. Will this have to be called every time we modify the... Let's see. Models are now ready for inference. We have their data set ready here. Let's see. Let's enter here. Whoops. Enter here. Build the generator. Target token. Yeah, obviously the only problem is when we're training on multiple. Yeah, when we're training on multiple language directions, you'd have to build a ton of these different generators for every particular language, right? which becomes quickly infeasible. So that's kind of the downside of this. Huh. Okay. And then build the generator here. So model, target dictionary, beam length, length penalty, source, match source length, and then the extra arguments. Okay. Is there any mentioning of the language here? No. No, okay. So build the tokenizer. And then let's see, we don't care about the actual inference step, get the hypotheses. Okay. Sample. So for one sample at a time, we do what? Target tokens. We grab them from the sample, we convert them to strings. We decode. Okay. And then we go to the hypotheses and then we do this. Okay. We can probably simplify this and run it, but will it be feasible, guys? Should we do this? Should we? I think we should literally take like 50 sentences, 50 English sentences, and translate them into the foreign language that we are training for, and just log that every like 2000 steps or something. And then, let me think, maybe like every 5000 steps we can go and compute all of the translations, and then just compute like Sacra Blue. If that makes sense. I'm not sure whether people do that, but I want to have that. Just a second. Okay. Let's try and do that. Let me see in the train scripts. I think we can do this until the end of the stream. So in the train script, we have some get iterator, epoch iterator is there. Epoch iterator. Okay, and what about What about validation? All that is in here. Validate and save. So we also pass in the epoch iterator. Which is also used we grab the next epoch iterator from here. We wrap it up into the progress bar, and then we use that one down there to train. So why does this one take the task and the epoch iterator? What does it do there? So it only because of the epoch. Well, and then epoch iterator validate. Get the validation iterator from the trainer. So they get from the trainer, they get the validation iterator. And then they use that one, they wrap it up here, and then they sample here. Okay, but we'll need a separate one. So what I'm going to do is literally take the functionality from here. We can stop this code. We can grab a lot of this here. Task. Load the task. Just a second. So how does this one know where to load from? Generate. Data is where it grabs. Okay, so it grabs the data from the shard here. Because we also have Flores there. How does it know to even use Flores? Wait, I'm a bit confused. Flores. Number of sentences. Okay, so this one does not know, but if we go to generate multi, if we go to its config, we have parsec model folder. Generate multi. Data is going to be here. So data directory. So here's the Flores path. Okay. So the Flores path is going to be passed somewhere here as a reference file. And then the reference file is generate command, generate data, put the results there. Let me see. Validation, model, generate. Huh. Config data. What do we set as the data path? This one. So how do we know here data bin shard 0? If we go to Stopes, what's this data bin shard 0 validation. Okay, so for all of these validation files are basically, all of them are Flores 200. That's how I've made them, how I've prepared this particular data here. So it's Flores 200 benchmark. Okay. So if that's the case, then we just have to we have to somehow specify the language when running generate multi. We do that by doing what? Generate multi. So this is our own repo now. We have to go back to persec. So generate multi. Okay, so we specify the source language and the target language. And that's how it's gonna use it. So let's go back to generate. So generate basically loads the iterator. We say which split we want. We say where is the path? Okay, just a second. Let's go to generate. So we specify this. Okay. Let's run it quickly once more. Generate, run. Go here. Go. Use CUDA, specify the task. All of that is good. Load the checkpoint. Load the dataset. Saved config task. What does this one specify? And does it specify any languages? It does. The data is here, the languages are here. Okay. So for us, this already happened, right? In the train loop as well. So we can just continue. Remove all of these. F5. Okay. Okay, so with this one, we grab the validation. and then okay, so that basically means we already have the right iterator. So what we need to do is just build the generator, grab the tokenizer. What's the tokenizer here, by the way? Nothing. Let's get here. Go here. Generation. Extra generation class. Keyword arguments is going to be specified right here. Like this. And then we build the generator. And then tokenizer is none. What do we do with none? What do we do with none? Choice, none. Return none. Okay, tokenizer is none. And then BPE is sentence piece. So we build the BPE. Encoders build BPE. Sentence piece. Config. Class, and then we build it. Okay, let's just try and do this. So models is gonna be, what's the format of that one? Models ensemble. Ensemble is just a list. Okay, let's go to generate. Let's grab this one. Let's open up train on the side. Train.py, whoops, train.py. Okay, and go to the right and then open up here open up the generate here. No bro, just open up generate. Okay, so how do we modify the train? Find the train step and then the validation step. So let's do something like, we can pack it inside here, or we can just externally add it. Do validate, call the validation, and inside there it's gonna grab the trainer to get the iterator. Okay, well, let's do it a bit differently. Let us train step. Let's do like this. So if I don't know, every some number of updates, if number of updates modulo, I don't know, 5,000 is 0, in that case we build the generator. We might need to optimize this, but let's just start somewhere. Let's grab this one. So this one looks like this. It's gonna be 0 here. This one looks like this. LM model is none, LM weight is 0. Do we even need it then? If this is just extra, where is it specified later? Where is it used? Is it already default value? Let's just see whether this is already default value so I know what to specify. Let me rerun the generate and just end up here. Rerun the generate. So again, what we're trying to do is implement every now and then sample text as opposed to just figuring out the loss. Okay, here we are. What's the value of this? None. So if that exists, only then do we add something. Otherwise, we just have still this plain old, completely boring symbols to strip from output. When did we add symbols to strip from output? Wait. When did that happen? We have here exactly 2 keys. And then we pass it exactly here. And then we do what? We come here. And the only thing that happens is here. When did this happen? Wait. Stop this again. Rerun. Okay. Length 2. Enter here. Aha. Symbols to script. Okay, let's then do the same thing here. Self data manager. Get decoder lang token. Is that called anywhere in train? Get decoder lang token. No, it's called in this manager. Let's see what happens in the manager. What's this self manager? It's inside of the task. It's something inside of the task. So if we okay, but we don't care about this because we're calling. Okay, sorry guys. I think we can just do it like this. Let's go to generate. This is all we need. Let's just specify it here. It's going to be equal to none here. Make sure we have equivalent code. So 0. We passed it here. Config generation is not going to be probably specified here. And models is going to be a list of the, where is our model? Where is our model? So here's a sample, here's a trainer. Where is the actual model? Do we even pass the model here? No, we don't, but it should be inside of task, right? I think task, we do something like this, task model. Does the task create a model? Okay. Build model retrieves back the model. Okay, let's go here back again and just understand what's going on. Stop this. Start the actual train. Let's start the train and see what happens. Okay. Build the model. So that one is going to return back the model. What do we do with the model here? We log it. We pass it into the trainer. Okay, I think the trainer has the model. So the trainer has the model. Yes. Okay, just self_model. So let's go back here. To our weird piece of code. Let's look for this one. Okay, so trainer. And then _model. We pass it in there. Generation. Config generation. Is here. And what's the, how does one call this? Get the generation parser. How can we specify this in train? Hey Veldon, I didn't see your message. Do you have experience of writing inference on CPP? I do have some experience with C++. I do have some experience analyzing CUDA kernels, but I never had to really write or optimize CUDA kernels myself. Okay. Can we get generation? There's a ton of arguments here. I'm just trying to now replicate all of the necessary, everything that's inside of config generate. So let's just reconstruct that by basically running, oops, not that. Stop that. Pick the generate, rerun. Let's just see what do we have in the config. What do we have specified here? What's this? Again, if we just plot it here, we just dump it as a quick hack. We can literally just do this and then save this here. Just want to make sure stuff is working. Just copy this and then config generation is equal to this, and then we pass in that one directly here. Now we have the same thing going on. Okay, I think. And now with the generator, we have to put it into the inference step. So we first have to, I guess, convert put the model to do the model into eval mode. Models is this, and then models here. Okay, and then the sample is going to happen here. Okay, so let's see, what do we need to do? How do they specify For validation, let's just put eval let's run train quickly. I just need to find one line. This is going to be my anchor, so I can search for this piece of code. Okay, waiting for train to hit this particular line. What's going on? Wait. So train, this run. Okay, F5, F5, go to the train step. Come on. Enter. Okay, so self in the actual trainer, we call the self model trained. So now we want to go, we actually want to call here. I guess it should be model here then. Okay, then we quickly do the following thing. Trainer model set to eval, and then at the end we can just leave it as it is because this one will set to train. Set it to train, put it in there, and then now we want to go and iterate by doing what? By, let me just stop the code. Stop the code, please stop. Okay. And then just open up generate here, generate. So in the train, let's find the validation. Where is that? This is not the right one. Okay, validate step. Nope, it's not there. Let's open it up here. Validate and step. It just takes some practice. It's hard to explain verbally. As anything else, you just build muscles to do it, right? It never gets easy, by the way. I don't think so. Config. Okay, so this is how they grab the validation iterator. So we want to grab this one. And then you can wrap that up into the progress bar, potentially, but you don't have to. Epoch prefix, we don't really need it. So given the progress, then we just iterate through it. And okay, so now we're gonna do the following. We're gonna go, just do the following. We grab the iterator. So here we just set valid and go push it back here. And now we go for, and we go to generate and then find sample. Let's see where it is. Okay, so here it is. Okay, so for sample in iterator, we do the following. We move the sample to CUDA. Do we do that same thing here? When we go and do validation and save, when we go and call validate, when we start iterating through samples, we enter here validation step, and then in the validation step you prepare the sample, right? And you prepare the sample by pushing it, converting it into so what's going to be the difference here? Is this one going to be FP32 or what? Let's just quickly see the difference here. So if we run generate until here, let's see what's the format of this sample. Okay. Hey Bollywood, Bollywood Musty. Yes, of course. Join the Open NLLB channel here, and you'll find everything you need, really. You'll find the pinned posts here. You'll find the language champion document. You'll find the getting started document here. That helps you understand how to get started, apparently. Just read through this and you'll see a bunch of things you can help with. And that's it. As simple as that. Thanks for showing interest. Let me hit F5. Let's get to the point where we sample, actually. So now we move to, okay, so what's the actual, what's going to be the data type here? So sample, if we grab like net input, and then we grab source tokens, what's going to be the actual D type? Int 64, which makes sense. These are, yeah, why would we even think, why would they even think that this will do anything else? So prepare sample. If it's none, okay, then we ignore. Convert. Why would we convert a sample? Just a second. If the D type is this, then we convert to, yeah, okay. So we don't care about this, actually. We just have to push to the GPU. So that means we go to train here. And then we just do this, move to CUDA, that's cool. And then after that, we do the following. Prefix tokens. Okay, we just do, we generate hypotheses like this. By the way, this is gonna be none, and constraints is gonna be none. So that means we end up with something like this. And then once we have hypotheses, then we can talk. For now, let's just print it. Okay, guys. Looking good. I made some mistake here, some stupid mistake. Okay, I see it, I see it, I see it. This should not be here. This should be here. And then print typos, and we're done. Your name is Meet, and you're going for masters in Germany. Yes, I join the server, and because I don't want to be the bottleneck for such questions as well. We have here channels like for job offers, information, interviewing. People are gonna be happy to help you out as well. Read my blogs. I kind of gave the answers to all of those questions. Basically, try and find a way to stand out somehow, either through GitHub projects. Like contributing to an open source project is definitely a good way to stand out, because most people don't do that. Most people just focus on getting a diploma. Okay, so let's try and run this. Let's quickly try and run this. No worries. You're not bothering me. It's just I'm trying to focus on this, so it's hard to bifurcate. But I try my best to reply ad hoc. But you can definitely find more if you join the server. Okay, let's just dump this in here and not even put this. Let's just not have any guard. Just do it like this directly. And now let me stop this. What might be problematic is that here we're using FSDP, whereas in the generate here, when we create the model here is just load ensemble. Will that be FSDP? I doubt it. This one will not be FSDP, right? This is gonna be just what we ensemble, append the model, which is what loaded state dictionary build model. So that's the pure model, not the FSDP model. And maybe we can obviously do this only on a single GPU. We can create some guard that says, hey, if you're rank 0, in that case you can run this or something like that. Let me see what makes sense. Hope you guys are not hope you guys don't mind that I'm just eating all of these Serbian cookies. It's called plasma, by the way. It's one of the best products my country has to offer. And cheap talent. Okay, let's go. Let me just make sure this makes sense. That's a complicated sentence. Okay, let's just use it as it is. Put the model t-val. Put it here. Will this crash? Let's see. So the models, what are we expecting from them? Self dictionary's lang is none. Here, none. Where did we fail? Somewhere. Let's see where. So rerun this again. Okay. What's going on? This is definitely something is off here. Let's see what. Number of updates. Guess next. Train inner. How do we prevent? How do we make only one of these models enter here? And the other one should be waiting. Not sure what's going on. Let's see. Why is this complaining? I didn't do anything, really. Okay, again, run this, stop this, and then rerun. Where's the second one? Okay. Eval. Go here. Grab the second one. Eval. Go here. Okay. Now enter here. Data manager. Okay, so it's failing there because it's failing. Why? That's a good advice. I agree. I'm not sure why this is. Let me just see. What's the difference between generate and here? What's the difference between generate and this? Okay. Run. Run. Go here. Grab the second model. Grab the second one. Go. Enter into this. So data manager. Why is the target language not specified? The target language is not specified because we can temporarily specify it or something. This is inside of the task. It's not specified because we're running training, right? And because of that, we basically don't have one target language. We have multiple. What does this decoder lang token do? get the lang token. Okay, let's just see how this works in generate, where we know it works because we specify the target language here. So here's the target language, Hindeva. So if we go to generate, it's gonna be here. Let's run with generate configs, kick it off. Okay. Enter. Here we are. Let's just enter here. So this is going to be specified and this is specified. So we enter here. We are inside of data multilingual data manager. So with the target token and this being set to multilingual and this being target, we enter here. Token styles is a dictionary, and then depending of what we end with, we grab multilingual and we get a style like this, and then we format the language. So it looks like this, and then we get the target dictionary and we pass in this to get the language token. So for the target dictionary of language, it retrieves it back and then get token index. Given the dictionary and the token, we just grab the index and make sure it's not unknown, and then we retrieve it back. And then having that, we can now add it to this and build the generator. So if we specified ad hoc the task args, then we could, let's go to the init of this task. And so args are just going to be stored somewhere, right? Setup data manager. This one will be doing what? Calling this, and then just specifying args here. How can we do this? If we specify I want to ad hoc modify the target language. That's what I'm trying to do. Not sure how we can do that though. I could hard code it temporarily just to make sure it works. So if we go here, I could temporarily hack this. Wait, let me just stop this. I didn't pick the right config. Train, go to train, kick it off. Okay. Okay. Let's go. Waiting for the second model. Okay. Let me enter. So we are now in build generator of this particular task. Translation multi-simple epoch. So we have to grab its self args. We have to go and grab its up there task. We have to grab the task, grab the args, and say target language is this and that. I mean, it's very hikey, but that's what I'm trying to do. I'm just trying to get something to work. Okay. So before this, we have to do something like this. Task args, target language, and let's set it to whatever it is that we're trying to currently get the validation iterator for. And we're actually, let's specify this as like Hindi Deva. And let's hard code here. I think we have to do something like, okay, we'll see how exactly these are called. Valid subsets. So let's grab like and put valid subset of 1 here. Let's just hard code it for the time being. And I think that one is like Hindi Deva. So now with this should work. Let's rerun. Let's just rerun. Run here. Whoops. What happened? Again, I just want to run this. Stop. Rerun. Okay, it's progressing. Let's go. Will this fail? It will not. Okay, that's cool. So now let's see this. Aha, so we actually have to specify second. Okay, that was my mistake. Well, let's see first whether this works. Enter here. And this is specified as Hindeva. So we grab the right token. And can we actually build here? Will something else now fail? This should work, this should work. Args looking good because we passed them in. That's okay. I'm not sure about this models. I just passed in a list and I have an FSTP there. So unfortunately nothing is labeled. We have no idea what this should be. This should be a, okay, this would be a list of fairsec models. So FSDP might cause us issues. Let's go and see. Let's just see what's going on. hit the 5, run, all the way until beam, target dictionary. It's always going to be the same because we're using SPM. Sequence generator, models, target. Let's just hit F5 to get here and then enter. Okay, so again, if it's instance of this, then do this. Otherwise, so we grab the, if it's an ensemble model, otherwise back this one into, grab the size, single model is this. I'm fairly sure this will not work just because we are backing in. Let's exit here. Okay, so let's exit. Let's exit. Okay, so it did not fail, but I'm fairly sure it's gonna fail very soon now that we have done this. We sample, we move to CUDA. Okay, there is a minor mistake here as well. Okay, but we are making progress, guys. We are making big progress. Okay, so we now have, this one is picking him data, so we're gonna iterate over that data, sample, and then generator models. Everything looks good. So the only fear is whether and how do I need to extract from FSDP, and I think I know that answer actually. If you go to the wrap, FSDP, wrap this one. So we just have to grab the model. Is going to be wrapped into this. How can we grab? Let's see how we can grab the model from that wrap once it's inside. Let's rerun this. Maybe we don't have to, but let's try. Maybe it will just work as it is. Okay. So enter here. Module, wrapper class, init, args. This one should be a model. Yes. Type, tuple, length 1. So if we go and do args of 0, what's the type of args of 0? This is the legacy transformer model. Okay. So once we go here, where is the module being packed into? Where is this module being saved to? Okay, so it's being deleted here and converted into internal shape, flattened. So it's going to be basically think, and then we get the parameters from it, and then we create the flatten, and then we delete it. So this might be a bit more difficult than I thought. Let's see. Hit F5. Remove this one. Okay, here we are. Build the generator, exit from here. Exit from here as well. Exit completely, exit completely. Here we are. Grab the data. And let's see what happens if we run inference. Boom. Fails because generator is struggling. Interesting. Move to CUDA. Maybe it's just due to the fact that we didn't run this properly. Let's see. We might be failing, but for a different reason than what I'm thinking we are failing for. Obviously, this is super hacky. And then at the end, we should put the task args to none, just because we are modifying it there. Okay. Move to CUDA. We'll do what? Device is 1. Go back here. See what's the value of the sample. Net input. Source tokens. Device CUDA index 1. Whereas the models are let's see. Enter here. Target token. Get the source. Expand the prefix. And then call generator. And that's it. That's it, but prefix token, 2 source tokens. So this one should also be on the CUDA, right? Device CUDA. So this is on CUDA. This is none. This is on CUDA. This is on CUDA. The model is FSDP. And it's likely not still on CUDA. Maybe that's a... Maybe we have to push generate here. Git annotate model sizes. We grab this source tokens. Okay. Beam size. Constraints. So far so good. Where does it fail? It fails likely here. Likely here. Forward encoder. Will this work? FSDP. refer to module logic, okay. Okay, return encoder. Okay, so return the non-scripted input and then do what? So the model, I guess, okay, this will actually work, guys. The only difference is we need to put this on the right device. How can I do this? So yeah, this will actually work. I think what we are missing here, is inside of train step, at one point we okay, let me comment this out. And let's get to the train step. Rerun train, making progress. Let's just see when does the conversion to CUDA, when do we push the model to CUDA? Enter here. Model train. Let's see. Prepare. Okay. We pass in the model. Enter. Model train. Why? Wait. When do we push the model to CUDA? What's the difference there? Huh. Okay, something's weird. So I misinterpreted something apparently. Let's go to train again. So train step. Definitely not the point where this happens. Begin epoch. It would definitely make sense to do it before the train starts. But where? And if it happened, then why are we having any issues? Yeah, I think the model should be pushed to the device, to the right device already. It might be just a weird misleading error. Let's see, let's rerun this. Let's go. Enter. Enter. Build the model. And then enter the rep. Build the model. Do we have any mention of CUDA in this argument section here. Local SGD. We do one thing quickly. String args like this, easier to search. Quickly just put it anywhere. CUDA device. Pipeline device. Pipeline encoder devices. Device ID. Pipeline. Okay. Definitely not what I... There is no mention of where to put this model to. So that means this model will be and once we wrap it, then we have these keyword arguments, which are empty. So when do we actually push the model? So not here, then when? Exit from here. Let's just exit. Exit. Okay, definitely does not happen there. Then when does it happen? Let's see. When do we actually push the model to the device? There is a ton of minor details, guys. Run until here. Okay, train step. Let's go inside. It's still not on the GPU. So it's gonna happen literally on the fly. Prepare the sample. And then here on the fly, I'm looking at the memory, nothing changed. The device is still not on the right device. So only when we enter here will we go to forward and then rebuild full. Not even there. Okay, we have to grab the second one, otherwise we'll fail. Let's just put the breakpoint here. Oh my god. That's the thing with frameworks. Lack of flexibility. You get the initial bump, but then it's just a mess. Can't even stop the run. Super annoying. Let me see. Run train again. Run. Okay, trainer, run. We don't need breakpoint there. Let's just run until we hit the forward of the FSTP. Okay, here it is. I just want to see the line where it does it. Okay, we are done. Okay, this is the wrong place for the checkpoint. Now I've passed it. I should have just hit F5 to go to the second iteration instead of decided to rerun everything and then I have to wait again. Let's go. Almost there. Waiting to hit this line. Here we are. Open up my tracking of the memory. Rebuild full. And then go here. Enter. It's completely abstracted away where to device. Where does this happen? To post reduction. Look, there's probably some of the hooks there. Okay, worst case. I don't want to even bother with this. Let's just stop this. Let's go to train. And let's go to our code. And let's uncomment it. And let's just remove this. So now both are on the CPU or whatever. So let's run this again. Let's go. Here we are. Run until print. Something else failed. Aha. Torch embeddings. Requiring a storage of 4096 are out of bounds for storage of size 0. Huh. I swear to God, I'm just going to comment this out and just build a model without fully sharded. Or maybe just like that. Okay, let's just try that. Okay, then we have to go to here. And just remove the fully sharded. Okay, will this work? So what's your device? CUDA index here. What's your device? CPU. Huh. Why is the input on the CPU and wait? Okay, then try and do this. Rerun. Good night, SQ. Have a good night, man. I'll be wrapping up in 5 minutes myself. It's midnight here in 4 minutes. Let me just wrap up this one, see whether this works. Without FSDP. I just want to make sure this works. Okay, I hear the sound. I hear the sound. Guys, I think it worked, but yeah. Apparently this worked. And for all of 48, we have 5. Awesome, 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 awesome. So this works. We just have to now find ways. Okay, tomorrow I'm gonna wrap this up in the morning. Let's get this thing working. So let's enable us to sample during the training. And then additionally, we're going to use that to do Sacra Blue evaluation. So we're going to have, other than loss, also those different metrics and qualitative result samples. That's it. I think that was good work. As I said, for tomorrow, we're going to wrap it up. Let me just add that to do here. So next steps. Is this one. And then maybe this one. Okay. September 8th. On 17th, I'll have to go to China. So that's going to be a little bit of a down period for a couple of days, for a week. but hopefully during that period I can get us some compute so we can get training this thing on big compute. How do you mean, SQ? You missed them because you didn't know I have them, or what? Okay, let me stop this. Let me just share with the people in Discord here the progress. Oh, you just had to work, of course. Makes sense. Okay, in a nutshell, they use source token contributions to figure out contributions to the output tokens to figure out whether the model is hallucinating. If the source contribution is insignificant, that means the model is hallucinating, in a nutshell. Okay, guys. See you tomorrow. Tomorrow I don't have any meetings or anything, so I'm gonna be on schedule. Let me see. So exactly 10:30 tomorrow AM, I'm going to start streaming until 3 PM. So schedule for tomorrow, 10:30 AM through 3 PM. I just put it's Central European time, and then 3:30 PM through basically 6:30 PM, and then 8:30 PM through midnight. Okay, that's it, guys. Have a nice evening, have a nice day, have a nice morning wherever you are, and catch you tomorrow. Cheers, guys. Bye, SQ. Good night.